So it's our great pleasure to have Deniz Ali Kaptan as our last speaker of joint number theory meeting, and he will talk on, well, I mean, maybe he will introduce the title of his talk. Yeah, please, Deniz Ali.
Greetings. It's my pleasure to be here. I thank the organizers for inviting me. I'm going to be talking about the evolution of ideas from the method of Goldstone, Pintz, and Yildirim to Maynard-Tao. It's a bird's eye view of the ideas. It's going to be quite colloquial, and for those unfamiliar to this line of investigation, I hope it will be interesting. So I will be using pen and paper, and I'll switch to my camera. I hope my resolution and whatnot is good. So it all starts with the twin prime conjecture. I'm sure everyone is familiar with this. It states that there are infinitely many prime pairs of primes differing by 2. So here, this conjecture is very well supported by computational observations. So, and there are more specific versions predicting asymptotics, which are also corroborated by whatever we can compute. And you can here replace 2 by 4 or 6, and you still find them as you expect to. However, of course, if you replace this 2 by 1, it doesn't work. Why? There are not infinitely many pairs of primes differing by 1, because for every n, either n or n plus 1 is divisible by 2. So the only n for which n and n plus 1 can be simultaneously prime is when n is 2 itself and the other is 3, and you can't have any other ones because they will always be, one of them will be an even number, which is not 2, so it will not be a prime. This rather trivial obstacle admits a generalization, and that notion is called admissibility. Let H be a set of k numbers. A set of k integers. We say that H is admissible if, when we reduce every element of H mod P for a prime, so the set of Hi mod P's, the size of the set is strictly less than P for all primes P. In other words, these numbers should not occupy all the residue classes mod P for a prime. We can find infinitely many primes differing by 2, or so it appears, since n plus 0 and n plus 2 0 and 2, this two-tuple pair, mod 2, they occupy the same residue class, so they don't occupy two residue classes, so it's fine. And of course, we don't need to check for any other primes greater than the size of the tuple, than this trivially holds. Therefore, this is admissible. However, 0, 1 is not admissible because when we reduce these mod 2, they do occupy all the residue classes mod 2. So this notion captures why this works for even numbers and not for odd numbers, and generalizes it. So for instance, you don't expect to find infinitely many triples of primes and n plus 2, n plus 4, because they then occupy all residue classes mod 3, even though they occupy only one residue class mod 2. However, if you adjust it a bit, then in this situation, we expect to find infinitely many n such that these three numbers are simultaneously primes. And this more generalized conjecture is called the prime k-tuple conjecture. It says that if h1 dot 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 hk is an admissible k-tuple, then there exist infinitely many n such that n plus h1 up to n plus hk are simultaneously primes. So, of course, this is way out of reach, even the twin prime conjecture is. So, at the outset, the history of the investigation of this problem started with compromises. The first compromise might be to aim for not even the twin prime conjecture with the constant 2, but so there's the bounded gap, let me say X conjecture, was there exists infinitely many n such that the difference between Pn plus 1 and Pn is bounded by some C. There exists a C such that, of course. So this might be the first relaxation of the twin prime conjecture. So effectively to do it not with 2, but any number. But this was also intractable. Now, if you're going to look for something weaker than this is investigating the gaps between consecutive primes. So the prime number theorem states that pi x is asymptotic to x log x, which implies in particular that the average gap between two primes is about log Pn. So a trivial consequence of this is if you divide this difference by the average gap, then take the inferior limit, this should be at most 1. So investigation started by putting stronger upper bounds, trying to put stronger upper bounds on this. So I'll show you a list of results of how such bounds evolved. Uh, this investigation was basically initiated by Hardy and Littlewood in 1926. They were able to establish that, by the way, this quantity is customarily called delta. So they could show that this is at most 2/3 on GRH. So GRH is needed because they work with L functions to consider arithmetic progressions, and they couldn't prove an unconditional result, but using GRH, they obtained this. Ranking refined their methods and tightened the result a bit. Still on GRH, obtained delta at most 3/5. Erdős was the first to come up with an unconditional bound less than 1 strictly, but the bound was unspecified even though it was effective. And Bombieri and Davenport in 1966, using the Bombieri-Vinogradov theorem, which Bombieri proved for this purpose actually, using that theorem, they were able to show that delta is at most 0.46 something. And this Bombieri-Vinogradov theorem basically substitutes for GRH. So practically replaces it in this application. Huxley improved that result a bit. Meyer developed still along these lines, a technical refinement which led to some significant improvements. And basically this was the state of affairs up until the result of Goldstone, Pintz, and Yildirim. And now I'm going to describe their approach. So the GPY setup. Suppose our aim is just to find 2 primes in a K tuple. So we have the tuple given. And first, given any n, start by counting the primes among n shifted by this tuple. So this is, I denote by this the characteristic function of primes. So we count the primes among n plus hi, basically, using this expression. From this count, subtract just 1 and multiply it by some weight. This weight function should be non-negative. And go ahead and sum this over some dyadic interval. Now, if you showed such a thing is positive, since these are non-negative, if you never had even 2 primes in a tuple, this would be either 0 or -1, so this thing would be negative. So if you show this is positive for n large enough, then this implies that at least for 1n between capital N and 2 capital N, there are at least 2 primes among the n plus hi. So this is the goal. Now, what should this Wn look like? This object is large when there are many primes among these, and small at its smallest, it's -1 when there are none. So you want this weighing to amplify the cases where you find many primes. So basically a good weight function should be concentrated on those n for which there are many primes among the n plus hi. Now, taking a cue from the classical proof of the prime number theorem, recall that it goes through an analysis of, well, the von Mangold function is defined to be log p when n is some power of a prime p and 0 otherwise. Therefore, if you sum lambda n up to x, the primes will provide the greatest contribution, because squares or higher powers of primes only come from primes up to square root x, cube root x, etc. So the main term in this is basically the sum over primes up to x of their logarithms. So the higher powers contribute negligibly. And this is roughly the count of primes weighted by logs. So if you show this is about x, then you show that pi x is asymptotic to x over log x. So this is the weight, so to speak, used in the classical proof of the prime number theorem. So the most natural analog to consider might be to define a lambda n h by lambda n plus h1 lambda n plus hk. So you could expect that this will be mainly concentrated on tuples where each component is a prime. Of course, this is a bit like begging the question, because if you could evaluate such things, estimate sums of such things easily, then you could just go ahead and directly derive asymptotics. So this is intractable. Dealing with these is rather prohibitive. And here's an approximation. We have lambda n equal to, this is by Möbius inversion, the sum over divisors of n of mu d log n over d. Now, if you introduce a smoothing to this, So truncate it up to some parameter r. So you restrict d to run up to r at most, and you replace this by r2, so it's a smooth truncation. And introduce this truncated thing. Then it turns out that if you form lambda r and h, which is a product of these lambda r's, then this is more workable. And Goldstone and Yildirim used such weights to show that lambda is at most a quarter. This fell just a bit short of breaking the record, but as it was a fundamentally novel approach, it generated due excitement and eventually would evolve to the Goldstone-Yildirim method. Now, to arrive at that, there is the so-called generalized von Mangold function, lambda k, which is the sum over divisors of n of mu d log n over d to the k. This has the property that this is supported on n with no more than k distinct prime factors. Then, if you form the product of the components of your tuple, call it P and H, and this is simply the product of these things. And feed this into the generalized von Mangold function. This will be 0 when this has more than k prime factors. When this has precisely k prime factors, again, the contribution from proper powers of primes can be expected to be negligible, as in the proof of the prime number theorem. So mostly what you will be detecting is prime tuples. Again, to make this more workable, you smoothly truncate it and form lambda kr or rk. Now this is a more promising sort of weight, but this also wasn't enough to completely settle the so-called small gap conjecture, which is to show that delta is 0. This is the aim. There's one final trick. We can't even find 2 primes at the moment. So aiming for a full tuple of primes is a bit too greedy. We would be happy just to detect 2 primes. Now, we would detect 2 primes, essentially, if we instead considered k plus l. So use the generalized von Mangold function, the k plus l I don't know how to say that in English. K plus L. I don't know. So if L is smaller than K minus 1, the components which receive more than 2 primes will still leave out 2 components with a single prime by basically the pigeonhole principle. So considering this allows you still to deduce that there's more than 1 prime without being too greedy, and the freedom afforded by this parameter improves your estimates when it comes to the technicality of things. And essentially with this, of course, this led to showing that delta is 0. Of course, another thing is needed because if you can simply show that something like this is greater than 0, then it means you find bounded gaps because your h is fixed. So what they ended up doing is further average this over all tuples, all admissible tuples with diameter at most epsilon log n. So the whole thing becomes, at least for one k tuple with diameter such and such, there's at least one n such that there are at least 2 primes here. That's the form of the estimate they obtain, which is enough to deduce that delta is that delta is exactly 0. Now, I should also talk about the role played by the Bombieri-Vinogradov theorem. It's a very essential ingredient in these. So, of course, to ensure that your weight is non-negative, in the end, you have to square these things. Basically, when you expand these, distribute these WNs and split it into 2 sums, assume Wn is given by a sum over divisors of n of something. It's not important what it is. Squared. When you distribute that weight and obtain 2 sums, the forms of the sums you have are the following. You have the sum over n up to 2n of this thing, your weight, and you have the same, except this time weighted by primes. You have AP n plus hj, let's say, and again this squared divisor sum. So working with this is not much of a problem. You simply expand the square and you rearrange sums. What you get is a sum over dn e of lambda d lambda e and a sum over n such that the least common multiple of these B and E divides them. There's no problem dealing with this. When you do the same with this kind of sum, then you actually have a prime characteristic function here. Essentially, what this is doing is you're counting primes in a given residue class mod DE between n and 2n. That's what it's doing. Count primes that are HJ, that are congruent to HJ mod DE between n and 2n. And now remember that I omitted it, but these are also bound by the parameter R we introduced. So this least common multiple of DE is at most R squared. Now we have the prime number theorem for arithmetic progressions, but when the modulus isn't quite small compared to n, the error terms start to dominate and you don't get asymptotics. So if you had to invoke the prime number theorem for arithmetic progressions to deal with this, you would have to require R at most a power of log n, which does quite badly. Now the Bombier-Vinogradov theorem states it allows you to essentially replace such a sum. So when you, I don't want to write, well, let me write the entire thing. So Bombier-Vinogradov theorem basically states that if you sum over all residues up to some power of x and take the maximum over all residue classes of all reduced residues mod q and consider the error in substituting the expected main term from the prime number theorem by pi x, I mean pi x q a. This is the count of primes up to x, which are a mod q. And what you expect is this should be x over 5q log x. So when you sum all these errors, on average, they are small. That's what the Bombier-Vinogradov theorem says. Well, it says it with, this is true for theta 1/2 and any epsilon. A theta for which such an estimate is true is called the level of distribution of primes. So you can use Bombier-Vinogradov to handle this because they will be summed over all such DAs. So you can be satisfied with only handling the average of the errors and not individual errors. So when you apply this, you require that R square should be at most n to the 1/2 minus epsilon. So you can take R to be roughly the fourth root of n. The larger you can take such a parameter, the better your results get. Therefore, it is very sensitive to this. And actually, the results of the method of Goldstone-Pintz yıldırım is if you could move just a little past level of distribution 1/2, then you get bounded gaps. And the Elliott-Halberstam conjecture predicts that theta can be taken to be 1. And if they assume that, they actually get infinitely many primes differing by 16. So, Soundarajan did a sort of meta-analysis of this method and assumed that you're working with weights of the form mu d times some polynomial of R over D, log R over D. And working with this unspecified polynomials derives, he showed that actually this method boils down to, for such an f, a polynomial, to show that this is greater than 1. And he also showed that the choice of Goldstone-Pintz and yıldırım was essentially best possible. Here, little x is what I've been writing as capital N. So this x is my previous capital N. And this shows how sensitive this is to R. It can be shown that this is almost 4 at most. This optimization problem gives you that. And when you can take R to be almost a quarter, you get almost 1. So with the averaging over the tuples trick I mentioned, you barely get delta equals 0. So this was the state of things around 2008-9, and it was a revolutionary result. It generated much excitement. Around that time, I applied this to number fields. So this was a theorem I proved. In a totally number field, OK is the ring of integers of the number field. So if the norms of the differences of two prime elements divided by log norm of 1, so it's the perfect analog of it. This was required because the analog of the Bombieri-Vinogradov theorem for number fields loses strength with the number of complex embeddings. Therefore, to actually have level of distribution 1/2, you have to be totally real. Therefore, this was required for this result. This was in 2013. Soon after came along the method of Maynard and Tao. Actually, I should mention first Zhang proved that the difference between consecutive primes is at most 70 million infinitely often. And he settled the bounded gap conjecture, which was, of course, a huge development. What he did was he used a refinement of the Bombieri-Vinogradov theorem, which applied to only a certain subclass of the moduli, some smooth moduli, those moduli having small prime factors, and he could restrict the evaluations to only caring about those, and he could squeeze out for those moduli. He proved a Bombieri-Vinogradov analog which went beyond distribution level of distribution 1/2, and he was able to prove this. And the polymath project led by Maynard-Tao optimized this down to something like 4,000-ish when Maynard came along, and he proved that the n plus first prime minus the nth prime is at most 600 infinitely open. And eventually this was reduced to 246, again by a polymath project led by Tao. Tao also developed this approach, which led to this independently, but he didn't publish around the same time. So the method which leads to this is called the Maynard-Tao method. And it's actually a very simple refinement of the GPY method, but it leads to dramatic improvements in the results. So remember, we had basically weights of the form d divides, well, p and h, where this was the product of the factors, and we had mu d and some function f log r over d. In some of the pages I forgot to put the products here, and I just wrote n, but in fact the whole point was to generalize the generalized von Mangold function to detect at most k plus l primes here. So I should have written this in 2 pages back. So we had this sort of thing designed to detect at most k plus l primes in a product. So then you have no control over which product receives what. So this is a one-dimensional divisor sum, so to say. The Maynard-Tao refinement is basically take a k-dimensional sum d1 up to dk such that di divides the corresponding component, and each is bounded. And take also a multi-dimensional, multivariable function correspondingly. this is it. Of course, by that time, the analysis of sound erosion was well known and studied. So with this move, the original GPY method had the analogy with the prime number theorem and also the Riemann zeta function kind of embedded into it. But with this optimization problem observation of sound erosion, and with this step, the connection with zeta is pretty much nowhere to be seen here. This produces a different optimization problem where you have much wider flexibility due to the number of variables. So when you apply a similar sort of reduction to an optimization problem, this happens to be what you get. Now you don't only exceed 1, you can exceed any number because this time you have a k here. And by simply taking large tuples, you can find as many primes as you like. This is a hugely dramatic improvement, and it can also prove that Pn plus R minus Pn is bounded infinitely often. So this was way out of reach in the preceding method. So yeah, this was the revolution this method introduced, and it was applied to many generalizations. The generalization of the number field results I talked about was also done. I applied it to arithmetic progressions. So this one's a bit of a mouthful. So while it's here for you to see, I'll talk about it on the side. So if you take a fixed arithmetic progression, modifying the method and arriving at bounded gaps is trivial. But you can take the following perspective. Suppose this interval is given with x large enough, and you want to be able to find gaps which are small in a prescribed fashion among primes in many arithmetic progressions here. So you try to describe a set of Q such that if Q is at most something in terms of x, then when x is large enough, you always find primes that are A mod Q in this interval, which are close. So from that perspective, this is a sort of a uniform bound for gaps and primes in arithmetic progressions. The way it reads is, I didn't write all the subcases because depending on the rate of growth of this bound, how large you're allowed to take Q, you have to allow some exceptions, which come from exceptional zeros of L functions. But suppose you have this bound, then for all Q up to that bound, by the way, this is an absolute x to the 5 over 12 minus epsilon, you can't exceed that. You may admit exceptions, but they are little of fx. So this is valid for almost all moduli. Then you can find a prime here in the arithmetic progression you're interested in, such that their difference is at most a constant times the moduli. The constant, of course, depends on this bound and how many primes you want to find. So that was basically the generalization to arithmetic progressions of Maynard-Tao's results. There was a very similar result in its formulation by Baker and Zhao. So they proved a similar result with stronger bounds as fx approaches this limit. However, they admitted a lot of exceptions. So this result is true for almost all moduli, while theirs was true for almost none. So they were, but with significantly stronger bounds as fx approaches this absolute bound. So this was a sort of complementary result from around roughly the same time. And that concludes what I wanted to say, and thank you. Is Professor Ikeda disconnected, I wonder? Something's going on in the chat. I suppose, does anyone have questions or?
It looks that there is no question or comments.
Yeah.
Okay, let's thanks the speaker for.
Thank you. Semi.
Or there is some question. Okay, there is.
All right. In that case, thank you for the opportunity to talk.
Thank
in
you
this
very much.
organization.
Thank you very much again.